All right, we're back recording. Here we go. All the questions should be in order, straight from that page I just gave you guys. First question: an object thrown in the air with the spin rotates about what point? Well, it's just for you guys. Well, it'll eventually be, guys. You know, 50 out of 100 questions are the same questions on the final exam. So yeah, it's really help you guys. Yeah, center of gravity, center of mass. This point spins back. Right. So if you guys remember when we came back from the break in January, we were doing rotational mechanics. Okay.
Does that answer go on to?
Yeah, I would rewrite these down. Yeah, it's the very first question, isn't it? Very first question. Yeah, an object thrown in the air with a spin rotates about. Yeah.
This could be on Google Classroom.
Yeah, I can put them on there. Yeah, I can do that. Yes. All right. All right. All right, getting some points. Points. Picture hangs on a wall from a wire passed over the supporting nail. The picture is in stable equilibrium because.
Nothing.
Yeah, all the above there. Right, so the center of gravity of the picture is directly below the supporting nail. That's true. After any small push, it will return to its original position. Any slight push would be raising its center of gravity. Yeah, those all go hand in hand. They all support being in stable equilibrium. Right, you guys go with stable equilibrium. Oh, and here, okay. Also, you guys have this picture. Right, that could be helpful too.
Yeah.
So, it looks like this one right here. What makes up that stable? More points. Points. Four. Force times lever arm. Force times lever arm. Okay. Here, it's this right here. So R cross F. Right? So this R cross with this F. Right? And cross product means that you're really only multiplying the perpendicular components. That's where the sine theta bit comes from. Right? So it's this R and, well, F sine theta, if you like. Right? Wouldn't that get the wrench to turn? Right? Don't you always push a door perpendicular to the surface of the door? Right? Okay. Force times lever R. If you open a door, the lever arm is the distance between the hinges and wherever you're pushing it. All right. Getting the points. You try loosening a nut with the wrench. The nut doesn't give it at all. You should what? Yeah, all of those would be helpful. Exert a larger force. If you make sure that you are pushing actually perpendicular, because I know if I push parallel to the wrench, no way does it ever turn. Right? And the more perpendicular I push, that helps me out, increases that cross product. Okay? You can also make the lever arm longer. If you have a pipe, you could slip that over the end of the wrench. That could extend the lever arm. That could be a way to do it. Yeah, so all of those would help you get more torque. So you guys know how to get more torque. Right? Boom, boom, boom. I bet somebody here is going to run into this situation one day. It's going to remember, oh yeah, that's right. I can do any of these things. And yeah. Resistance an object has to change in its rotational state of motion is called rotational. Ooh. Inertia, rotational inertia. Yeah, rotational inertia. You guys remember these meter stick? Actually, I still got them over there. They're over on that table. And you could feel these shaking back and forth. Guess which one of these, the left picture or the right picture, is much easier to shake back and forth? Yeah, the left picture. You know, if you pick them up both up blindfolded, they feel like the same mass and the same weight. But yeah, right, this picture on the right is more difficult right, because the mass is further out. So some of them are squared. That's called rotational inertia. Right, you guys remember rotational inertia? Right. How about this? If a bowling ball versus a basketball is rolling downhill, right? The different rotational inertia. Right? They roll down differently. Bowling ball beats the basketball. Gymnast moves from an extended position to a tucked position. Ooh. Yeah, it would be decreasing your rotational inertia. Right. Now, the another principle involved here is called conservation of angular momentum. And because angular momentum is conserved, if you decrease this I right here, rotational inertia, what happens to your angular velocity? Yeah, the angular velocity would increase, right? It's like this figure skater here going from the extended to tuck position would spin faster, wouldn't it? Right? Spin faster. Right, so there's a little more to that question too. Right, guys, get there. Get there. We got that? Well, object will maintain its angular momentum unless acted on by an unbalanced force or torque. Yeah, that's also called conservation of angular momentum. You guys, Sierra spinning one revolution every 24 hours? Yeah, will that be true 100 years from now? Yep, because there's basically nothing external slowing it down. Yeah, true 100 years ago, true 100 years from now. It's just spinning. That's angular moment. That's conservation of angular momentum. Yeah, conservation of angular momentum. When an ice skater pulls his hands in to turn faster. Yeah, those are all true. They all go together. All right, so going from that picture on the left to picture on the right, your rotational inertia decreases. Angular momentum is overall conserved. Therefore, your angular velocity would increase. Yeah, all three of those. All three of those. Huge rotating cloud of particles in space gravitates together. Ooh, this sounds really similar. As it shrinks in size. Yeah, it's going to rotate faster. Yeah. Just like the ice skater. It's the same physics. Right? So conservation of angular momentum. Yeah. Right, that makes sense why that would be. All right, that's good. Two people sit on a balanced seesaw. When one person leans forward, that person's end will.
No, I.
Will rise. Will rise. Yeah, let's go back and look at that picture. You get this. Right. So what if this is all about actually that looks pretty well balanced there, doesn't it? Right. The torque sums to zero, so on. Right. What if this person on the left side starts walking in towards the center? Right. Like if you walked all the way to the center. Right. Now the counterclockwise torque is gone. Right. And now you only have the clockwise torque, so the whole thing turns clockwise. You guys see that? Right. Right. Well, go back to the beginning. Where it's balanced. If this person simply leans forward, it does get closer to that situation. Yeah, so the whole thing would have to turn clockwise a little bit. Yeah, you guys see that? Or turn that way. Right. Right, makes sense. Makes sense.
The box method? Box method. Yes, the method.
When used horizontally in construction, an I-beam is nearly as strong as a solid bar because
That's 7. Oh, the box.
yeah, the tension and compression are primarily in the top and bottom parts. Here, go back to this picture. Actually, you know, I do want to draw this one up for you guys. Do that here. Draw this out. Okay, so we got the ivy. Like this.
You're so.
It has some length,
But.
whole thing. Alright, so there's your ivy. Okay. And what if I have this on a couple supports? I put a support there on that end, and then all the way on the other end. Well, there's another support over here. Kind of see it here a little bit. Okay, so you guys see my two supports on the ends? I'm gonna put a huge weight in the middle. A huge weight right here. Huge force. Okay. So these are all forces, right? A couple support forces and a huge weight in the middle. Yes, doesn't that make the whole thing want to bend like this from the side? If I look at this cross section on the side, it wants to bend like a smiley face. Isn't that true? Right. Whole thing wants to bend. Bend like that. Okay. Okay. So how about this little section right here, this little square? Would this be in tension or compression?
Oh, no,
Here, suppose you take a sponge and you bend it like this.
wait a minute.
You guys see at the bottom part? Yeah, it would be trying to pull apart in tension. You guys see that? Same thing? Yeah, guys, this is in tension. This is being pulled apart. Okay. But what about this little square in the top? What's going on there?
Oh.
Yeah, that's a compression, isn't it? Okay, so the bottom of this is in tension, the top's a compression. You guys see that?
Yeah.
Okay. Now, if you fall through piece by piece, going from the bottom to the top, right? It switches over from tension to compression. So all tension here, all compression at the top. Okay. But right in the middle, there's a point where there's neither tension nor compression. It all cancels out. There's like some nodal line here, so there's neither nor. Okay. Oh, okay, so it looks like the vast majority of tension and compression are in the top and the bottom. So that's where you want to put most of the steel, most of the material. All right, and that'll carry the load. Yeah. Plus, it weighs less. It's more economical. Yeah. So those would also be good reasons. Yeah. There's your physics reason right there. All right. That makes sense.
You're fine.
All right.
Well,
Tension compression predominantly in the top and bottom. Less force is required to poke through an eggshell from.
Oh. Oh.
Yeah, there you go. There you go. Yeah. It's easier to be the baby tick trying to get out than it is trying to be a predator trying to get in. Right. And it had to do with the physics of arches. Right. So here's a Cadmere version. So this is just one version of this. Good famous version, right? But yeah, say if you see a compression bridge, or like a compression arch bridge, right? If you stand in the middle of that bridge, the forces are transferred right into that arch and into the ground. Which geometrical shape has the least surface area for a given volume? Yeah, it turns out a sphere. Oh, draw this for you. We have a pyramid, cube, sphere, cylinder. Draw those. Here's a pyramid, something like that. We had a cube. Right, there was a cube. There's a sphere. And a cylinder. Yes. Okay. Okay. So suppose you had oh yeah, ignore the ID, I guess. Okay. Okay. Guys, suppose you have some blob of Play-Doh, right? You guys see you have a blob of Play-Doh here, right? And you want to form it into some shape, and you want to paint it, but you want to use the least amount of paint. Right? You want to minimize the surface area for some given blob of Play-Doh. You guys get that? You want to minimize the surface area. Right? Yeah, the sphere is the one that's going to do it. This is what's going to minimize the surface area for some given volume. Okay. Or if you turn that around and said, I have some amount of paint, I want some designated surface area, and I want to maximize the volume of the surface area, that would also be the sphere. Okay. The sphere, the ratio of surface area to volume is minimized. Right. All right, you guys go to the sphere. Sphere.
You.
Right. Man, I know about that.
What? Why?
Which will cool water faster? Ice cubes or the same mass of ice crushed? Yeah, crush will cool it faster. Why? Guys, why does the crushed ice cool water faster than the solid ice cube? It does. It has more surface area. Okay. So here, if I go to this picture, okay, if that was like a giant cube, there would be so much surface area, which would have something to do with like how fast can that cube absorb thermal energy from the surrounding water. But yeah, if you slice it up into a bunch of little tiny cubes, right, yeah, now you can access like what used to be inside the big cube. So yeah, that's more surface area. That's a faster transfer of thermal energy. Okay. So you guys go to the crushed ice, has more surface area. All right, you guys are all taking notes on this? Because I'm giving you all the, well, give you a bunch of final exam answers. Hold up. If an elephant grows to twice its height, the area of its ears would change by a factor of.
I think he is. What do you say?
Yeah, factor of 4. Now, why a factor of 4? Because, guys, look at this question. The surface area of its ears, surface area. Okay. Guys, is that like this middle one right here? Surface area? Okay. So, no, they said grows to twice its height. So instead of a factor of 3, like matching the picture, could you just change the space value to 2? Is that okay? It's 2 squared. That's what it is. You're twice as tall. Tall is a linear factor. Okay. And the question is about surface area of its ears, which is a squared value. So it's a factor of 2 squared. 2 squared is 4. Okay? That's why it's 4. Okay. Here, do you guys know here? This actually goes hand in hand with the next question. It's what if you start with a small animal? Right? Let's have a little mouse right here. Right? And then you go to a big animal, like say elephant. It's your classic big animal, right? Yeah. Got big elephant feet up there. All right. All right, so I got a mouse versus an elephant. Okay. Guys, the mouse has some volume of mouse, right? And the elephant has some volume of an elephant a little bit, right? They also have surface areas. Okay, so if you look at the surface area, I'll call it SA for surface area of the mouse versus the surface area for the elephant. Okay, and what if you take that ratio, the ratio of surface area compared to volume? Okay, so you guys get that surface area compared to volume? Okay. Oh, which ratio? Which ratio is the bigger ratio? The mouse or the elephant? Huh. Okay. Sure. Let's go back and look at this diagram here. This one right here. Okay. Guys, could this little box down here represent the mouse and this big old crate represent the elephant? You think? Okay. Okay, so let's say it's 1 unit by 1 unit, unit by 1 unit. So the mouse has a volume of 1 cubic unit there. Okay. And the elephant is 3 times as tall, but has how many times the volume? 27. Wow. Guys, do you guys see if you're 3 times as tall, you have 27 times the volume, but you only have how many times the surface area? 9. So what's growing faster, the surface area or the volume? The volume's growing way faster, way faster. Okay. Which means this volume right here is huge. So I think it has to go this way. Okay. This particular ratio is larger for the mouse. Okay. Oh. Okay. So really, do you guys see that? If you stand back and look at this proportion, okay, like these are both warm-blooded animals. You guys know we have to all maintain constant body temperature. Like for humans, it's some value. For any of these animals, it's some value, right? And it looks like what the elephant really needs is more surface area compared to its volume. You guys see that? Okay, so how could it do that? Oh, well, getting have really, really huge ears, and that will make it a lot easier to radiate away excess heat. Ah, yeah. Little biology tie in there. Do you guys follow that? Because I think the next question is a pretty similar question. Yeah, there we go. Elephant grows to twice its normal height. Will increase its weight by a factor of. Did you guys get okay? 8. Right. Let's see where 8 comes from. Because where I'm putting 3 here, 3, 3, 3, that just matches this picture. You guys see my cube's been scaled by a linear factor of 3. Right. But the question you guys get here about the elephant is double its original height. Isn't that a linear scale of 2? So we're gonna replace this base value with 2. Right. Now this question is about weight. Guys, is weight proportional to mass? Yeah.
Yeah.
Right. So weight is mg. Yeah. And does mass occupy volume?
Yeah.
Yeah. So really, this is a volume related question, isn't it? So let's look at volume. Because what happens when you take a base value of 2 and you put it in 2 dimensions, or sorry, 3 dimensions?
8.
8. You get 8. You guys see where 8 comes from? It's 2 to the power of 3. You guys see 2 to the power of 3 is the answer? Right there, right? Everybody knows the answer is 2 to the power of 3? Right. So on the actual final exam, this question might be worded a little bit different. It might say the elephant grows 4 times as tall. And as long as you know the principle behind it, then you'll be good. Yeah. So the numbers are allowed to change a little bit on the final exam. Otherwise, you'll see the same set of questions. Where is pressure greater? 1 meter beneath the surface of Lake Michigan or 1 meter beneath the surface of a swimming pond? Yeah, it's the same pressure. Right? Okay, so here, go back to here. I did update this one a little bit, so it might look a little different. Okay. This left picture is buoyant force. That's not the question, though. The question is about pressure. Here's your pressure formula. So it's the density of the surrounding fluid, in this case water, the gravity field of the planet, and H represents how deep you dive. So rho GH. Right? Well, 1 meter deep is the same, could be the same for a swimming pond as it is for the lake, and these other numbers are the same also. Yeah, it's the same pressure. Same pressure. Right? You guys go with same pressure? Same pressure. We're just 1 meter down from the surface. Archimedes' principle says an object is buoyed up by a force that is equal to the weight of the fluid displaced. Weight of the fluid displaced. Okay. That's the only even possibly correct answer just from the words. Okay. Guys, force. We're looking for a force, right? A force. Okay. Is a weight a type of force? Is that true? Is a weight a type of force? Yeah. Okay. Is a mass a type of force? No. Is a volume a type of force? No. Right. Now let's look at that picture again. Right, this one right here. Okay. So buoyant force. You guys remember Archimedes' principle of buoyant force? Rho Vg. Okay. So density of the water times volume displaced. Okay. Now that together represents the mass of the water displaced. And then if you multiply that by the gravity field of the planet. Right. I remember mg represents a force. That's right. So that would be the weight of the water displaced. Right. So look at this picture too. If I have a 10 Newton weight, dunk into water, now the force rate, the tension rating goes down to 7. And I've captured 3 newtons weight of water. Okay. Isn't weight measured in newtons? That's right. Right, you guys go with weight of fluid displaced. Good. Archimedes' principle. Reason objects in a fluid experience an upward buoyant force is because pressure is greatest on the bottom. Yeah, that'd be true. Yeah. And so why is it you jump in a swimming pool, you naturally want to float to the top? Why doesn't it push you to the bottom or something, right? Yeah, because the deeper you go, the more the pressure is. Now there's a pressure differential, so overall the direction of the force would be upward. Yeah, that is a true statement. True statement. Boom, 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 boom. You squeeze a balloon to half its original size, the pressure inside the balloon increases by a factor of 2. Here, you guys see this ideal gas law? Pressure volume equals NR and then absolute temperature. Okay, no. All right, here, let's take a look at this. So I got a balloon. Right? I'm gonna squeeze it down. So now it's only half of its original volume. Okay, there's a fly flying around on the inside. Okay. Set up a PV equals nRT. Okay. Now since the balloon is sealed and is stuck as a constant, that's the number of gas molecules. R itself is a constant, so that's the same. And let's say that the temperature is pretty well the same too. So this is all stuck at some constant, all right? This balloon had some pressure inside and some volume. Okay. And to make it really easy, can I just call all these one? Can I say 1 times 1 equals 1, 1, 1? I mean, if you had the matching units, you could craft an equation like that. That would be okay, right? Okay. And now that I'm going to make this volume half of what it used to be, and all these numbers on the right side are just locked in place anyway. Okay. Guys, what's the only number I can put right here to balance this equation? 2. Is it 2 times a half? Balances the equation? Okay. Or if you like this version of the story, what if you're the fly flying around inside? Do you feel that if somebody's smashing out the balloon, you can feel the pressure increasing? This would be a factor of 2. Yeah, that's it. A balloon is buoyed up with a force equal to the weight of air that the balloon displaces. And density and pressure are totally different units anyway. So if we're looking for a force, okay, weight looks like a good start. Okay. The weight of the balloon is trying to pull it down. The weight of the air it displaces is holding it up. Okay. That's Archimedes' principle all over again. You guys good with Archimedes' principle? Okay. A balloon is buoyed up with a force equal to the weight of the displaced air. Okay. You guys go with weight of displaced air? Makes sense. Archimedes. A 2-ton dirigible hovers in the air. The buoyant force acting on it is 2 tons. Here, I'll draw that up for you guys. 2-ton dirigible. Okay. So we're talking about probably a blimp or maybe a hot air balloon or some version of that. Let's say we got a blimp going on. Okay, something like that. Okay. Let's do a free body diagram on this guy. Free body diagram. I think that the weight of this is trying to pull it down, and that was equal to 2 tons. Because if it's just hovering there at rest, isn't it true that the forces have to be balanced out? Yeah. So this is the buoyant force, which must also be equal to 2 tons, so that it's just hovering at rest. So that the sum of forces goes to 0 newtons. Or 0 tons, I guess, in this case. Sum of force 0. You guys go with sum of forces is 0. 2-ton buoyant force balances out a 2-ton weight. You're standing on the moon. You release a balloon filled with helium gas. What will that balloon do? Fall down to the ground. All right, let's look at Y here. Let's go Y. Right, so let's start on Earth, and then later on we'll go to the moon. Okay. So on Earth, I have this helium balloon. I'm going to drop the balloon on Earth. Okay. Okay, so this balloon have a little bit of weight. Yeah, it's got a little bit of weight. But there's a much bigger force acting on it, and that's the buoyant force, F sub B, right? Because it's displacing some air, right? In fact, that helium doesn't weigh very much, so the buoyant force is going to beat the weight, and as soon as you let it go, zoom, it accelerates upward. But now let's go to the moon. Okay, so does this balloon have a little bit of weight on the moon? Yeah, it's actually 1/6 of what it was on Earth, so but it is a tiny weight, tiny weight. But does the moon have an atmosphere? No. So can there be a buoyant force?
No.
No. That's all. That's it. So you release the balloon here, and it's gonna fall straight down. Fall straight down. All right, you guys go. You drop anything on the moon, it's gonna just free fall straight down. River narrows. The water in the river flows. Yeah, the linear speed is faster. Right. So the principle is conservation of flow. So the flow rate's the same, but the linear speed, if you could measure that, it would have to speed up. This is actually this cold box here. Right. So you guys remember if the pipe system narrows, the water speeds up. Guys remember that? You blow across the top of a piece of paper. What's that paper do? Yeah, doesn't it vacuum up? Because you guys remember fast moving fluids cause a decrease in pressure. Isn't that Bernoulli principle? Right. Oftentimes we also connected that with conservation of flow. So if you have a wide pipe leading to a skinny pipe, the water has to speed up. The fact that water speeds up, you run this equation right here, and you can show that the pressure decreases. That's the same thing. You can try this too. I did this in class too. You blow across the top piece of paper, doesn't it? It vacuums up because that decreases the pressure where you have the flowing air. Lifts up. You can try that. That's what it'll do. Temperature is mostly related to yeah, I'm looking for average molecular kinetic energy. So how hot or cold does something feel? Right, so the theory here goes, if you could zoom down to the atomic scale, if you saw those atoms vibrating very quickly, that would correspond to a high temperature. If they were vibrating more slowly, that would correspond to a lower temperature, right? And it wouldn't matter how much material there is. What matters is, like, on average, how fast are the molecules vibrating, right? You could have a small cup of water that's 50 degrees Fahrenheit, or you could have a large bowl of water that's 50 degrees Fahrenheit. Okay. And even though it's different amounts of water, if they're the same temperature, I bet their molecules on average are vibrating at the same speed. Okay. You guys go with average molecular kinetic energy? All right. Good, good. Everybody good. Reason an ocean's temperature does not vary much from season to season is yeah, look for a high specific heat capacity of water. Right? Like compared to most other materials, water has a really high heat capacity. It's very, very difficult to change the temperature of water. Here, if I go back to this picture, it's like the reciprocal of the slope of this line. Right? Like you guys know, if you put a metal pot on the stove filled with water, doesn't the metal part of the pot heat up very quickly? But it takes a few minutes for the water to heat up, right? And then if you turn off the stove, then the metal will cool down relatively quickly, but maybe that water will stay warm for a long time, right? So it takes a lot of energy transfer to change the temperature a little bit for water. Yeah. The temperature of water is very, very stable because it has a high specific heat capacity. Okay? That makes sense.
Of course.
The largest extremes in temperature are usually experienced. Oh, and there's the numerical values of these things. So here's liquid water. Yeah, middle of continents. Right, where do you guys see all these other options are near large bodies of water? Right, islands, oceans, coastal. Right, we got large bodies of water nearby. Right, and water, the temperature is relatively stable. But yeah, anybody been out to the Midwest in the States? Yeah, you can have crazy temperature swings. It could be like 90 degrees Fahrenheit in the day, and then like drop way, way down at night. Right, so nothing like Florida. Florida's relatively stable. We're surrounded by water. An iron ring is heated uniformly. The whole becomes Yeah, also larger, right? So the entire object expands, including the hole in the middle, like the donut hole. Right, yeah, so you guys remember that one. Right, so most materials you heat them, they expand, including metals. All right. During a very cold winter, water pipes sometimes burst. Why? Yeah, water expands when it freezes. It's also a weird property of water, right? Most materials, that they go from a liquid to a solid state, that tend to occupy less volume, but water's the opposite, right? You guys know that because you guys know that ice cubes will float in a glass of water, or icebergs will float in the ocean. Yeah, that ice is less dense than the liquid water. Right? But then, if you have a pipe filled with water and you freeze it, ooh, well, you could burst the pipe. Uh, Nobody ever puts a sealed Coke can in the freezer, do they? Well, at least you wouldn't do that for very long because it'll explode the can. Heat transfer by conduction in metals occurs when conduction. Uh, yeah, so electrons bump into atoms and other electrons. That's direct contact. Okay. So you guys know there's three main types of heat transfer. Conduction is direct contact, okay. But really, anything you directly touch isn't just electron clouds against electron clouds, right? Like if you pick up a pencil and start writing with it, the electrons on the surface of your skin are touching the electrons of the pencil. Yeah. Okay. So direct contact, direct contact. Okay. This gold one's radiation. This blue one looks like convection. Okay. All right, we got a few questions left here. Just enough time. Heat transfer by convection. Uh, yeah, large numbers of atoms move place to place. Sometimes called convection currents. Right. Guys, if you have a pot of water heating on the stove, isn't it true the bottom of the water would get hot and the top of the water would be relatively cool? Right. But that initiates a convection current. And then the water starts to move and transfer thermal energy within the water mass. So that evens out the temperature. Right. So you get bulk movement of fluids. That's called convection. Heat travels from the sun to Earth.
Vi har last year så English
Yeah, radiation. There you go. Okay. So how does sunlight reach the Earth through the vacuum of space? Isn't that the only form of thermal energy transfer through a vacuum? It'd be radiation, right? Yeah, radiation. And last question for today. You guys ready for last question? Last question. How does planet Earth lose heat?
Yeah.
Well, also radiation. Hey guys, isn't Earth surrounded by the vacuum of space? Right. So we're importing thermal energy from the sun. Right? There's also geothermal that can add, right? But then it radiates away that energy, and ideally, of course, everything's supposed to stay in a form of a balance. All right. So we got. All right. I've got Larper, Anna, Goyum Cattle. All right. So nice job. We'll pick up there tomorrow.